Section 1.3 is simply titled More on Functions and Their Graphs. So what is meant by that, what we'll be doing in this section, you'll see in the objectives here, we're going to look at determining when a function is increasing, decreasing, and constant. We'll do that by looking at a graph and then putting increasing, decreasing, and constant in interval notations. And then we'll use a graph to determine any relative maxima or minima, any high and low points. We'll test for symmetry, whether it's symmetric about the origin or symmetric about the y-axis. We'll identify even or odd functions, and we can tell even and odd functions by their symmetry and also by the powers within the equation. We'll be talking about that. And then we'll understand and use piecewise function. That's a topic that I see some students struggle with, so make sure you get that in this section. And then by far the most important part of this section, and it's the last part of the homework, is to find and simplify a function's difference quotient. That has some strong calculus ramifications in the future, so I'll really want to focus on making sure you're comfortable with the difference quotient problems. Now, first of all, starting off with the easy stuff, if we talk about increasing, decreasing, and constant, we simply say a function is increasing on an interval L if f of x1 is less than f of x2 whenever x1 is less than x2. And then for any x1 and x2 in the interval. So all that means, as you're moving from left to right on the x-axis, your function has to be going up. So if x2 is greater than x1, then the y value at x2 has to be greater than the y value at x1. A function is decreasing on an interval L if f of x1 is greater than f of x2 whenever x1 is less than x2. So x1 is a point to the left of x2, but the y value at x1 is greater. Well, all that means is that your function is going down as you move from left to right on the x-axis. Anytime it's moving down as the function moves from left to right, of course it's decreasing. And then we say a function is constant anytime the y values do not change when the x values do change. Okay, now looking at this to answer some questions about increasing and decreasing. So a problem I see students make on something like this is they'll look at that arrow pointing downward and they'll say, oh, well, that has to mean decreasing, doesn't it? Of course not. Please think about that. As the function is moving from left to right, this function is increasing until it gets to this high point here at -1. So how am I supposed to answer that? Well, I can say as x starts at -infinity until x gets to -1, this function is going upwards. So you'll see I say it's increasing from -infinity to -1. Now, from x equals -1 until x is equal to 1, look what's happening on the function. It's moving down. So then you can say, well then, okay, it's decreasing from -1 to 1. That's what I have right here. And now, what happens right after x equals 1? Well, at x equals 1, it had a minimum, and then immediately after x equals 1, it started going up forever and ever and ever. How do I represent that? Well, it's going to be increasing when x is equal to 1 forevermore, so all the way to infinity. Good problem there. Now, talking about those relative maxima and minima, we can say that the point f of a, and notice that's a y value. The y values are always our maximum or minimum points. The function's value, f of a, is a relative maximum of the function f if there exists an open interval containing a such that f of a is greater than all the other values of f of x for all of x that's not equal to a in that open interval. So all that's saying is for any point to the left and right of x equals a, everything's going to be lower than the value of f of a itself. So it has to be higher than any point immediately around it. Now, on the other hand, for a relative minimum, it's just saying that f of b has to be less than f of x for all x that's not equal to b in the open interval around x. Okay, again, all that's saying is that f of b has to be lower than any y value immediately around it. Okay, well, that would be a minimum. Now, please keep in mind, it's not saying it has to be the lowest point on the entire graph, nor is f of a for the maximum, saying it's the highest point on the entire graph. It's just higher than any point immediately to its left or right, and minimum lower than any point to its immediate left or right. For example, if I go back to that exact same question that we had, if I were to ask you what's the absolute maximum or minimum of this function, there are none, because this function is going to continue to go to infinity and continue to go to negative infinity as it moves to the left. So there are no absolute maxima and minima, but it certainly does have a relative maximum and a relative minimum. You might have called these local maxima and local minima before. The words relative and local are interchangeable. Our book is using the terminology relative. So I can say at x equals -1, f of -1 is a maximum relative to any point immediately around it. Yeah, it's higher than any point immediately around it. It's my maximum point. So I can say f of -1 is my maximum, or I can say f has a relative maximum at x equals -1. We don't know the specific y value, so we just give the location of the maximum at -1. And then we can say f has a relative minimum at x equals 1, because at x equals 1, f of 1 is lower than any point immediately to its left or right. So we can have a relative minimum there. Now, definitions of even and odd functions. The function f is an even function if you can plug a -x in for x and it not change anything. So if f of x, or sorry, if f of -x is equal to f of x, for all x in the domain of f, it's an even function. The right side of the equation of an even function does not change if x is replaced with a -x. The graph of an even function is symmetric with respect to the x-axis. Now, that has to make sense to you. If you have the value, let's say, f of 5 is equal to 4. Well, if f of 5 is equal to 4, then f of -5 also must equal 4, because you can change the sign on x and it doesn't change the sign on y. And if that's the case, you're going to have a function that's nice and symmetric with respect to the y-axis. Now, if a function is symmetric to the origin, it's going to be an odd function. And an odd function occurs anytime you can say f of -x. If you change the sign on x, it changes the sign on the entire function for all x in the domain of f. For every term on the right-hand side of the equation, the odd function changes the sign of x when it's replaced with a -x. The graph of an odd function is symmetric with respect to the origin. So in this case, to use my other example where I said f of 5 is 4, well then if it's an odd function, then f of -5 would have to be -4. And I can say, okay, yeah, that's going to be whatever happens in quadrant 1, the same thing's going to happen equal and opposite in quadrant 3, similar with quadrant 2 and quadrant 4. Now, if we're identifying even and odd functions, it's really easy. All you have to do is look at your powers on the x. If every power on x is an odd number, and then it's going to be an odd function. If every power on x is an even number, then it's going to be an even function. That's going to work for all polynomials. Now, what tricks some people is constants in there. Remember, constant is understood to have an x with it, but that x would be to the 0 power, which is even. So before I even work this problem, I know it's neither, because you're going to have an x to the 5th and a 1x to the 0. One power is odd, the 0 power is even. What happens when you have both? It's neither even nor odd. I know that before I even look at it. But going ahead and plugging in our algebraic techniques, because it's good to work with that anyway, if I try h of -x, then you say, well, I'm going to have -x raised to the 5th, and then I'll have plus 1. Well, all right, -x raised to the 5th is the negative of x to the 5th. A negative to an odd power is a negative, but then I still have that plus 1. So when I'm looking at that, I can say, well, is this equal to the negative of the original function? No, the negative of the original function would be -x to the 5th minus 1. So I can say what that's telling me, since h of -x is not equal to h of x, it's not even. And also, it's not going to be odd because it's not the negative of the original function. So it's not even, nor is it odd, because It's just a combination of the two. So now I can say, all right, if I'm looking at piecewise functions here, a function that is defined by two or more equations over a specified domain is called a piecewise function. Let's look at an example of that. Here I'm giving you, this would be a simplistic cost function where I say C of t is going to equal 20. Now that's going to be anytime the number of values t that are produced is between 0 and 60, and that's inclusive of the endpoints. Now, the second part of this piecewise function occurs, well, what if t is going to exceed 60? Then it's saying, well, okay, then your function is going to be that original 20 plus 40 cents, you might think of it, or plus 0.4 times the number in excess of 60 by saying t minus 60. All right, so now if I have you evaluate this function c at 40, all you have to do is go into your function and say, well, all right, find out where I evaluate this at. Well, 40 falls in the first set of numbers between 0 and 60. So c of 40, you're just plugging it into that top equation where there's nothing to plug it into. You just say, well, c of 40 is clearly 20 then. But on the other hand, if I say c of 80, it's like, well, c evaluated at 80, now that's going to put me into the second part of this piecewise function. It's not defined for t equals 80 in the first part. So I plug 80 in for t in the second part, and I'll get 20 plus 0.4 times 80 minus 60. That gives me 0.4 times 20. So I have 20 plus 0.4 times 20. That's going to give me 20 plus 8 for 28. So I can see that you can double the amount produced in this case and only increase the cost by $8. Not bad. Now, if we're graphing a piecewise function, you need to look at where the domain for one part ends and where the domain for the other part begins. This piecewise function, it's always a constant function. F of x is equal to 3 until x gets to -1. It's saying y is equal to 3 for x is less than or equal to -1. And I know there's going to be a solid dot at the ordered pair -1, 3, because the function is defined to be 3 when x is -1. Now, on the other part of the graph, though, for all values x is greater than -1, it's just going to be the function x minus 2. I know that that's a function with a y-intercept at -2 and a slope of 1. Now, it's not technically defined at -1, but it would still be wise to plug -1 into this function because we need to show where this function begins. And in this case, when we plug a -1 into it, -1 minus 2, you can see when I plugged a -1 into it, I got a -3. Now, what do I know? I know that it's going to begin at the ordered pair -1, -3. What am I going to do at that ordered pair? I'm going to draw an open circle in the graph. It has to have a starting point, but in this case, the starting point for the second portion of this function is an open circle. But then instantly after -1, it starts being defined. All I have to do is plot one more point. I could plot the point 0, -2 after it, and then connect in my line after. You'll see that's what I did here. My first line was y is equal to 3 all until x got to -1, and it included when x was -1. I needed to start my second line when x was -1, so I plugged a -1 into this function, and I got -1 minus 2 is -3, so I can say, well, all right, that starts at the point -1, -3, but it's not defined for that line, so I put an open circle down there. Then I can say, well, all right, if I plug in x equals 0, I get 0 minus 2, a y-intercept of -2. I connect the open circle with that point, and then I could connect my line forever and ever after that. So then I would be done with my piecewise function. And please notice, it does pass the vertical line test because at any x value, there is only one y value. That's why you can't have a solid dot here and a solid dot here, because it wouldn't be a function, and this graph had to be a function. Now, my favorite topic of this section, gorgeousness, is the expression f of x plus h minus f of x over h. And this is where h cannot equal 0, obviously, or the quantity would not exist. This is called the difference quotient function, f. Now, this difference quotient is going to be very helpful in calculus as we start talking about an instantaneous rate of change. We say an instantaneous rate of change is nothing more than the instantaneous rate of change of y over x. Well, this f of x plus h minus f of x, it's just your y value at x plus h minus your y value at x, and then your denominator is just the distance between your two x values. Well, x plus h minus x, they're a distance of h units away. In calculus, what we will do is we'll take this expression and put a limit as h approaches 0 out in front of it, and that's going to find the instantaneous rate of change. We're not physically plugging a 0 in for h, but we're going to allow that h value to become infinitesimally small and look at what happens to it. In order to do that, you need to be able to algebraically simplify these expressions in a pre-calculus class. So let me start off with this and say, what if I give you the quadratic function f of x is equal to negative 2x squared plus x plus 5? And I'm wanting you to find and simplify the expression. Eventually, we'll look at f of x plus h minus f of x over h. On this page, I just wanted to really concentrate on letting you see what the f of x plus h is. F of x plus h, all it's telling you to do is replace each x in your function with an x plus h. So in the place of x squared, I put x plus h squared. Of course, in the place of x, I put an x plus h. Now, I need to go ahead and simplify that out. Please remember, x plus h squared is not simply, it's one of my pet peeves when students put, ooh, is that x squared plus h squared? Never, ever, ever. A binomial squared is always, always a trinomial. If you need to write out x plus h times x plus h and then FOIL it out to get to the correct terminology, that's fine. What you should, though, remember is that it's always going to be the square of the first term and then plus 2 times the first term times the last term. So it's going to be plus 2xh, and then it's plus the last term squared. And the reason it's that plus that 2xh is because you're going to have plus xh and then plus another hx, which is another plus xh. It's always going to be twice the first term times the second term for that middle term there. Now, of course, there's really nothing else to do in my problem. The x plus h, I just brought down, and then the plus 5. Now I distribute the negative 2 throughout that trinomial. I get negative 2x squared minus 4xh minus 2h squared. Then I have my plus x plus h plus 5. Now that is the simplified version of f of x plus h. Now I try to go ahead and plug it all into the difference quotient. F of x plus h, that's this part that I have right there. I just brought that from the last page. Normally in my homework, you'll see I keep a bracket around that just to show all of this is my f of x plus h. Now I'm subtracting from that f of x. Well, that's just your original function that you're subtracting, all over h. Now, something I want you to remember here is that the terms of f of x plus h and the terms of f of x will always, always cancel. They will never combine, never. So you can automatically here say, all right, well, if they're supposed to cancel, and I went ahead and showed out where I subtracted and changed the sign here. This step right here is really unnecessary. I'd almost rather you go from here to here and say, okay, if the terms always cancel, please look. Negative 2x squared minus a negative 2x squared cancels, just as I said they would always do. The plus x minus a plus x cancels. 5 minus 5 cancels. So you say, well, all three of these terms cancel with their corresponding terms over here. What's remaining? Well, what's remaining is you're going to have a negative 4xh minus a 2h squared plus an h. And then all of that still over h. Now, just like I promised, the terms will always cancel. Another thing that I promise will always work out in these problems is that any term that doesn't cancel out must, and I repeat, must have a factor of h. So I could have even went from this step direct to this step and say, I know every term in the numerator will have a factor of h that doesn't cancel. I'm going to factor that h out in this step. When I do, I'll get negative 4x minus 2h to the first, and then please don't make a mistake here, plus 1. I see a lot of people just ignore that last term. You can't ignore it. It's a plus 1. Please notice if I distributed the h back through, I'd get back this numerator. But now, why is this in superior format? Because you're not done with these difference quotient problems until you can eliminate. I can say I can eliminate because I can cancel the factor of h with the factor of h in the numerator. Gorgeousness. When I do that, it's going to leave me with the trinomial expression, negative 4x minus 2h plus 1 for my final answer. And now, again, that answer is really only valid if h does not equal 0. So we could see that from the very beginning of the problem. Of course, this difference quotient expression is not valid if h is equal to 0. So we say it's this answer or h is not 0. Now, please do really focus on the last portion of the homework problems. I tried to show out my work really well out of the problems I worked out of the book on my assignments. That's an extremely important set of problems I'm wanting to make sure you're comfortable with. All right, guys, that finishes the notes for this section. Please let me know if you have any questions. I'll be glad to help.